Okay, yeah, great to be here. Good afternoon to everyone. Thanks, Christian, for the invite. I'm Michael. Yes, I'm living in Germany, but actually originally from the UK, family originally from Scotland, hence the strange spelling of Michael. Yeah, and I am one of the three co-founders of ecoLocked. We founded ecoLocked. It's a Berlin-based climate tech startup. We founded in September 2021. And as of January this year, we are now a team of 14 full-time employees. And I'm going to talk to you a bit about what we're up to with Biochar and how we're using it as our main inputs to develop products or admixtures for the concrete industry. So our mission at ecoLocked is really to bring carbon removal to the gigaton scale. And how we're doing that is by turning captured carbon into valuable products for the construction industry. And as you know, the main inputs that we are using right now is biochar. I won't spend too long on this slide, but as many of you are aware, we have a growing problem. We need to scale up carbon removal significantly over the next couple of decades to reach 10 or more, at least 10 gigatons of CO2 per year by 2050, if we're going to have a fighting chance of mitigating the worst effects of climate change. And at ecoLocked, we strongly believe that the best way to do this is couple carbon storage with carbon utilization. Thereby, we not only enable additional the technology to extract CO2 from the atmosphere, but we're able to provide functionalized products to industry and at the same time ensure that long-term storage potential of the captured carbon. And one of the industries that's really struggling right now is the construction industry. It's around 40% of emissions are attributed to the built environment, 15% from the construction or the building materials. And concrete is quite an issue. It's responsible for around 8% of global greenhouse gas emissions from the production of the cement clinker. And just for some context, that's around 4 times greater in the aviation industry. So the construction industry needs solutions. However, the construction industry is notoriously conservative. It takes time to develop them. And what we need is solutions right now. We need solutions that don't take 10 to 15 years. And that's where we come in. So we can already store 4 gigatons, at least 4 gigatons of CO2 in the built environment. And not only can we store it there, it can then compensate for some of the residual emissions and provide functional performance improvements. So we can really utilize that CO2 when we use it to develop construction materials. And that's really what ecoLocked's all about. So we take solid carbon that's locked already atmospheric CO2 from various feedstocks in the form of biochar. We process it, we blend it, we optimize it, and we develop products for specific applications to address certain industry problems. So who are we? This is a complex area. We've assembled a fantastic team with 3 co-founders. I am the CTO, so I'm on the technical side and product development side, background in mechanical engineering and environmental sciences. And my 2 other co-founders, they're on the business side, both ex-business consultants with significant industry experience, business experience, Mario, CEO, and Steph on the commercial side. And the team, we have chemical engineers, we have civil engineers, material scientists, concrete technologists on the technical side, and then we have sales and business development split about 50-50. Right, into the topic. So what I like to start with is some of the challenges of using biochar in concrete. And I've pinched this from Mallinger et al. 2021. I like it because what they did is they mapped out the various interactions between the concrete mix chemistry and the biochar and how they're interlinked and how they all affect one another. And what you can see, it's just a mess. And what this means is that if you are looking for a cause and effect, you take one biochar, it has high ash, you put it in a concrete mix, you get a result. Can you figure out why you get that result when you take a different biochar and you get a different result? The answer is maybe. It takes a lot of data, a lot of analysis, but you can see that if you have multivariate analysis, it's hard to identify those causes. However, it's very important when we're talking about concrete, that we can ensure consistency, that we can ensure quality, and that we can predict a certain level of performance. So it's important to start with this, or being aware of this topic, and then how can we address it? How can we ensure that we don't get stuck here? Actually, there was a study that was conducted by the Colorado School of Mines over the last 2.5 years, and they took this problem in-house and they set to answer it. They took, I think, around 4 or 5 different biochars. They extensively tested, changing various parameters to try and isolate these variables that are really influential for concrete performance. And after a year of testing and analysis with the full team, they found that they could not isolate, or they could not find any significant effects using the standard regression models. They then didn't give up. They employed machine learning and they went deeper into the topic. And after another year, they found that there was 4 outputs. There was 4 significant influences, 3 of which were, I would say, quite predictable, and 1 spurious. So what it goes to show is that even when you really go into the data, it's very hard to isolate those variables. And so what are we doing about it at ecoLocked? We have been extensively testing, and we're building up our database and our library. And that's what we've forms the foundation for what we're calling the ecoLocked platform. And this is really our internal tool to ensure we can understand the differences between different biochars, how to optimize them, how they perform in different concrete mixtures and for different applications, and of course, how to process them to give consistent performance, optimized performance, and ultimately products that our customers are happy with. So on the left-hand side, you can see we have different input materials, biochars from different feedstocks across the full spectrum. We take those biochars, we build up the database of biochar chemical and physical characteristics. We have the database of performance, and then our platform is able to suggest then how to optimize those ready for the different product segments. So on the right-hand side, you can see what we're currently focused on. So that's ecoLocked materials for lightweight concrete. So replacing lightweight aggregates, paving slabs, ready-mix concrete, pigmented concrete, all of which have different composition, different processing, different blends of biochars plus other mineral additives. To go a little bit deeper of what we've been investigating in-house now, and these are the most important variables for us that we started with. So on the left-hand side, you can see, obviously, biochar type is hugely important to understand which biochars really do lend themselves well for these applications and which don't. Then we have the dosage, so how much of these materials can we get into the mix? And of course, then if we're adding a lot of biochar into a concrete, what is it replacing? What are we taking out? And in what ratios are we taking the ingredients out? Because actually, concrete mixes are quite sensitive to these different fluctuations. And if you know exactly how to use it and how to optimize these ratios, you can have significant improvement in the structural performance. Then we have how to use the water cement ratio. As everyone is aware, biochar is a highly porous material. It absorbs water very readily and holds it. And when it enters into a concrete mix, it immediately starts absorbing the free water in the mix, leading to a stiffer mix. It's harder to work with it. It cures faster, and this can have its benefits. But in the case of ready mix, when you're pumping concrete, it can have catastrophic effects. For example, if the concrete gets poured into a truck and then you can't get it out. So it's very important. And actually, you might think, it's easy, you just add more water. Well, adding more water, it leads to reduction in compressive strength quite quickly. And there's a threshold there. Controlling the volume. So this was a topic we hadn't thought about at the beginning. But depending on the material and how it's used, we've found that integrating biochar, depending on the amount, can do nothing to the volume, remains the same. It can increase it or it can reduce it. So understanding exactly what the volume is and predicting it so that when we deliver to our customers with the recipes, they know how to produce 1 cubic meter, because that's the measure for concrete. It's a volumetric measure. And we have particle size distribution and mixed chemistry, also very important. So the mixed chemistry, which type of cement, which the interactions with the biochar there, and the additives to enhance various other performance. So, for example, the use of superplasticizers. And how we assessing how we optimize for these variables, we have these indicators here, as I mentioned before, the biochar classifications, but then the concrete mechanical performance, strength, density, consistency, the setting time of the concrete. We're also looking at thermal conductivity, and the last two, permeability and freeze thaw. Well, these are very much durability driven indicators that we're assessing over the long term. It's not exhaustive. We are also looking into others, but this is our focus area, and what we have isolated as at least the foundational aspects to be aware of when looking to develop such a technology. And the images there, you can see these are taken from our lab, what we are currently doing every single day in the R&D team. To provide some data and some contextualization about what I'm just explaining, we have here, this is analysis we did to understand the effects of different biochars on the 28-day strength of concrete. And so each data point there is a different type of biochar. Different type of biochar also mean different feedstocks. So we have anything here from sewage sludges through to woods and anything in between. So agricultural crop residues. We have assessed food processing residues, nutshells, food wastes. It's all in there and assessed. And what you can see is that you do have this variability of performance. The good news is that most of the data falls quite close to the control line there, indicating that we can use different biochar feedstocks for these applications. It's then the next thing is understanding how to process these materials and optimize mix designs to bring up the performance as much as possible. So what is the point in doing all of this research, all this R&D, and understanding these materials and how they work in concrete? It's to produce our product ranges and sell to our customers to provide these climate-friendly solutions. So these are our current product ranges in development. We've released the first one, ecoLocked Material Zero, as it's called, ELM Zero. And this product really enables our customers to build with carbon neutral concrete whilst maintaining structural performance. So that's the goal of ELM Zero. We then are developing ELM Speed, Black and Light. These, as they suggest, the speed is focused on accelerating the curing time. This is really beneficial for our customers in the precast industry, so they can demold faster, they can produce more products and in the same time frame. ELM Black, this is one which might seem obvious. Well, biochar is obviously black, and this is a sought after color for concrete. Some of our partners, our concrete producers that we're working with, have around 1/3 of their product line containing some form of black pigmentation. So this is a great eco alternative. They can achieve the same color grades and at the same time store some atmospheric CO2 in the concrete. And ELM Light's focused on lightweight concrete, as it sounds. So this is replacing lightweight aggregates, which have also a very high CO2 footprint, to produce lightweight concrete, lightweight insulating concrete, I should mention. How do these products look like? Yeah, so this is ecoLocked Material Zero. We deliver the ecoLocked materials, which is then optimized for specific application of our customers. We've worked with a ready-mix concrete and also earth moist mixes, earth moist concrete for concrete pavers, and they are quite different. They have quite different requirements. So yeah, the ecoLocked materials is optimized depending on our customer application. Obviously, the optimized recipes, which I spoke about. And the third point to make is that we cover the impact management. So how can we ensure that this concrete is indeed carbon neutral, that we don't end up with falling into the trap of greenwashing? So we have verified LCAs and EPDs to demonstrate that actually the final product is as per the requirements. And on the right-hand side, this is how it works in practice. The concrete producers currently using standard ingredients. They integrate our materials as a drop-in solution, mix it along with the others as according to our prescribed order of addition and recipes. and they then can immediately start using that for whatever building projects are demanded. So here we have an example of some of our pilots and projects to date. To give you a little insight into how we've been using this technology. In the top left, you can see our project for ready-mix concrete. So this was 30 cubic meters of structural floor for a floor slab structural concrete, carbon neutral. And then some of the other pictures you can see with our paver producers. Again, carbon neutral pavers here. So this is the earth moist mix I was talking about. So it's not fluid, it's very, very dry, like sort of moist earth. And on the bottom there, you can see some street furniture. And this is currently where we're focused on for the time being. Mention that precast elements such as pavers and street furniture have lower, should we say, certification thresholds. So that's where we're focused on for the next couple of years, where we can really scale up without having to tackle the big topic of, the norms, the standards, and the certification. This is a very quick 1-minute video clip I wanted to show, detailing or giving a bit of more insight into how the ready-mix concrete project went. So this is the truck arriving with 7 cubic meters of carbon neutral concrete with our materials. This is a barn conversion. The before shot, here's the wet concrete. You can see it's flowing like any other ready-mix concrete, but apart from the color. Ground workers can install it as any other concrete, except they were a little shocked about how black it was. It took them a while to feel comfortable with that. And there we go. It's the finished articles there. And I should note that it cured in the same time as they're used to. So all in all, this was and we cast some cubes to check the strength, of course. And all in all, a very successful first project. And we've actually already retired those CO2 certificates that came with that project, first to be retired by Carbon Future, actually. I'll share again. Okay, so what's next for us? So we're currently raising capital. If anyone has any ideas or venture capital funds that they are aware of, want to put us in touch, would be greatly appreciated. We're setting up our production facility this year. It's already been engineered, and that's going to be coming online in the next 2 months. And that's at our lab and production site just outside Berlin. We're expanding our product catalog, as I explained, developing and improving our platform, so the functionality of our platform, so we can have more predictive capacity. We can develop products faster and reduce that product development cycles that take so long with concrete, whilst expanding and exploring new markets and growing our sales channels. On the product development side, that's continuous to develop these new products and verify them. And of course, R&D partnerships. We're always looking for new innovative ways to develop concrete with our biochars and our admixtures. Currently, we're working, for example, on looking at bioreactive concrete. So how can we use our materials in a concrete mix to actually grow algae on the facades of buildings that decrease the heat island effect, improve biodiversity, retain water, and so on. So if anyone is setting up any R&D consortiums and looking for an industry partner, then reach out to me. We don't have capacity to do any leading, but obviously would love to hear about joining anything that's relevant. And brings me to the end of my presentation. Thank you everyone for your attention, and happy to answer any questions you might have.
Great. Thank you very much, Micheil, also for being spot on with the time. So if there are any questions, write them into the chat or raise your hand and you can ask Micheil directly. So the first question, I think you answered it, but you can probably repeat it, was from Marshall. What are you using to make biochar, and how much biochar can you produce per day?
Yeah, so we're actually not producing biochar ourselves. We're using the already existing great biochar market industry. We can see that more and more biochar is coming online every year. So we are focused on what we do best, and that's developing these products and applications for biochar to enable the scale up of the industry. So what we do is we take raw materials, raw biochars, and we process them and optimize them for specific applications. In our production facility that we are that's coming online in the next couple of months, we'll have a capacity between 300 and 500 tons per year. And obviously that's our first kind of pilot plant, and that would be we'd be looking to scale it up this year and next year once we have started producing our first batches.
And I think a follow-up question from Martin was, which technology, are you technology agnostic, so only slow pyrolysis biochar or gasification char, or you don't mind your test and whichever works is fine?
We are, I wouldn't say technology agnostic, but we're as flexible as they come. So there are certain technologies. Thermal carbonization is one that has a big question mark over it. So some of the lower temperature, lower temperature technologies do not produce as stable material. So we have to just make sure, biochar stability is a big topic, but provided that the stability of the material can be ensured, then we are technology agnostic to that extent.
And to follow up on that, technology agnostic, but do you have any contamination limitations that you, I don't know how it is in concrete regarding heavy metals, or is that an issue in biochar mixing, or?
Actually, yes, it is. It depends on the application. If the concrete is going to be in contact with soils, we have to ensure that it's meeting the environmental regulations. So we perform leaching tests on the materials to ensure that they meet the environmental regulations. If it looks like there's could be an issue, and if it doesn't pass, then we would rule out that material for that application.
Okay. So questions coming. So Sean Thomas was asking, are there prospects for permeable concrete products? This would be a natural match given biochar porosity.
Yes, good question. We have looked into it. Actually, we had one of our students, he did his master's project with us on porous concrete as a means of water filtration. So we're constantly looking at ways to innovate and develop new products, and filtration concrete is definitely one that is earmarked for the future.
But I guess it will take quite some R&D to get it on the market. But it sounds like a great idea, actually, similar to the algae bioreactive concrete. So Dan Ranch was asking, how much uplift in cost is there compared to standard concrete? I guess you get this question regularly.
Yeah, it really depends on the application. So we're anywhere between 5 and 30% premium for our first products. And then beyond that, we can be cost competitive, if not cheaper, for some of the other products. Because, for example, if we're talking about competing in lightweight aggregate market, actually lightweight aggregates are fairly expensive and CO2 intensive. And so that's where we can really bring the cost down and provide economic solutions.
Okay, so we have to quickly go through the questions now. So Maria Pepper was asking, which regulation or test do you follow to ensure fire safety of the product for construction materials? Or do you have any issues with fire safety?
Yeah, we have not looked into it yet. We have a 1-year durability study that's kicking off this month, for which fire safety is one of the R&D streams. So ask me in a year. But I would say that there's quite a few papers published into the performance of concrete containing biochar, and what it points to is actually you can improve the temperature resistance of concrete with biochar, because what you have is you introduce reservoirs of expansion and contraction. So when you have the concrete heating up, any water or moisture trapped and that's what expands and then cracks the concrete, and it ultimately leads to failure. You have the reservoirs where it can actually expand. So biochar concrete tends, according to the literature, lasts longer in the case of fire than you would ordinary concrete.
Okay, that sounds promising. So I had to skip some of the questions, so sorry for that. Suvik was asking, for the slide you showed compressive strength results of concrete, specifically those that exceeded the 60 megapascal strength. What was the governing feature? Was this strength improvement due to the biochar feedstock properties, or could it be a result of concrete mix design? So what is more important, the biochar properties or your mixing?
It's all of the interaction there, and I mean, yeah, I'm not going to go into too much detail about the reasons, but yeah, it's a combination of the mix design optimization and the material optimization and the chemistry, the interacting chemistry.
Okay. So again, sorry for skipping some of the questions. Maybe Michael is around afterwards and can have a look at the chat. Vera Botten was asking, he's curious if specialty concrete mixtures for cold regions are considered.
For what, sorry?
On cold regions. So I guess very cold regions. We focus on reducing the curing times and temperatures.
Yes. So the ELM speed that we are developing will be able to affect the curing time. And what we've seen when we do our calorimetry studies is that we can increase the heat of hydration with some of our products. So that will have implications for curing in colder regions. But I really, the caveat there is this is really early stage, and we haven't released anything yet. Still in development again.
One very quick question. How much carbon can you sequester with 1 ton of biochar concrete?
1 ton of so roughly 1 ton of concrete. I mean, yeah, it depends. Well, you know, the formula is 1 ton of biochar, 3 tons of CO2. So it depends on the mix design in the end. And we have mix designs ranging from anywhere from 10 kilos per cubic meter up to 120, 130 kilos per cubic meter.
Okay, so that's a nice number, 120, so whatever kilograms of CO2. So the rest of the questions, please try to answer them afterwards in the chat. My last question would be, so what's the pain point right now for biochar in construction materials? Is it the price? Is it the regulations? Or is it just not there yet and we don't have any obstacles and it will be there in 2 years?
No, I think regulation is a big topic. I didn't touch on it in a lot of detail because there wasn't time. But it's definitely one that we are struggling with, and how it will go in the future. So we're looking to regulation to shift to recognize the voluntary carbon market and these CO2 certificates. We're looking for regulation to be more flexible when it comes to new construction materials. And the pricing, I would say, used to be more of a topic, but over the last 12 months, we've seen prices coming down, which is very, very promising. And if it continues like that, we are, we're in a good way for this technology.